Okay, so I'm going to try to catch up as much as possible on the chapter 36. I want to make one announcement in particular. Occasionally I will work a few problems out after they're due. People have told me that they don't really fully explain them sometimes. Well, certainly they don't do it in WebAssign, and occasionally they don't do it in Chegg either if you are using Chegg. And I hope if you, like I said, if you do, you use that sparingly, because it can be helpful, but it can also be dangerous. It can give you a false sense that if you don't work hard on the problems first. But anyway, two things I want to say is problems number 6 and number 8 from last week are on my door. So those were like a couple of the harder ones, and people had emailed me about that. So homework number 6 and 8 from chapter 35 on my door. Okay, so you can go there and look at it. And also, after exams, I will post solutions on my door as well. So anyway, if you want to take a look at that, you're welcome to. Okay, so what I want to do today is start with X-ray diffraction. And I'm going to start by drawing a picture. Now you have these handouts in front of you, so I'll be very sketchy on the whiteboard. But basically, the idea of X-ray diffraction is that notice that if you look at multi-slit diffraction, which is what we call diffraction gratings, right? Then I get the wavelength lambda of light is coming through here, and I'm looking on a distant screen, and the light emanates out in spherical wavelengths, right? And we calculate constructive or destructive interference by looking at rays from adjacent slits, and we came up with an empirical rule that we would get high intensity on the slit when d sine theta is equal to m times lambda, and m can be equal to 1, 2, 3, etc. Right? Now, okay, that was our first conclusion. Now, around the turn of the 19th or into the 20th century, early 1900s, two physicists, father and son, by the name of Bragg, discovered something called Bragg's law. And basically what they did was to say that if I consider a periodic array of atoms, and let's say there's only a few layers of them, but let's say this is what we call a cubic lattice. So this is called a cubic lattice, which means that you have to think of atoms at regular spacing d in all 3 dimensions. So the dimension between any two atoms, any adjacent atoms, closest atoms, is d, and that forms a simple cubic lattice. So everybody got that? It's a 3-dimensional point array on a grid with equal spacing. And those are the atomic sites. That's where the atoms are located. Right? Now, the idea that Bragg had was that if I have light of a certain wavelength, and notice one thing that we have always been using here is that the wavelengths and the spacing d are generally comparable. I mean, d can be of order up to, let's say, 1,000 times lambda in a lot of our examples, but they cannot be 20,000 or 100,000 or a million times larger than lambda. And so the basic idea was that the wavelength of light has to be sort of in the magnitude of the spacing d between the atoms to get interference. Now, the idea that they were promoting was that as the light, and by the way, these are light of, we're going to find out, very short wavelengths. The spacing d is of the order of 0.1 nanometers. Lambda is also of the order of 0.1 nanometers. So the spacing between atoms in a lattice is very small. And Bragg and his son hypothesized that the new phenomena at the time, which was called X-rays, consisted of electromagnetic radiation that was identical to light waves, except the wavelength is short. And they said, what if X-rays actually are another form of electromagnetic wave? With light, of course, the wavelength is 500 nanometers. With X-rays, it's much, much shorter. And they hypothesized that this is, in fact, what would happen. Now, if this was going to happen, could we make a diffraction interference phenomena that would verify that X-rays do, in fact, act like waves? Okay? And so their idea was that if we took a beam of X-rays, and every time it interacted with an atom in the crystal, it would absorb the X-rays would be absorbed, and then they would get re-emitted. Right? So in every one of these places where the light gets absorbed, it would also re-emit. Right? And it could re-emit from the first layer, from the second layer, from the third layer, and so forth. But the point is that they are emitting at regular spacing. So what you really have is something where light gets through. I didn't draw this quite exactly as the way I should. Let me try a different color. Let's say, for example, that I want to replace this array of this crystal with a slit experiment. So I put a slit like this, and light can only get through where I normally would have the crystal atomic centers. So light could actually, or radiation, we would say, would therefore emanate through the slit here, and they'd emanate through the slit here. And basically what I'm doing now is I am making a multi-slit apparatus. I am making a phenomena that looks exactly like the diffraction gradient. Only I'm doing it with a crystal lattice instead of a physical barrier of slits. Okay? So the regular periodic location of the atoms and the crystals, and remember they're in 3 dimensions, right? So I've got the cubic lattice extending out this way, so these really are slits of light that come through at, of course, discrete points along the slit. But nevertheless, it's a slit-like apparatus. Okay? So he hypothesized that that the crystal lattice acts like a diffraction gradient, and he hypothesized that the X-rays was a wave phenomenon of electromagnetic radiation. And if you put those two together, then you should be able to observe on a distant screen maximum and minimum that is very much like what we get with the I'm sorry I drew this so broad. I can make this. Remember, our point about diffraction is that the widths of the diffractions are very tiny and narrow. That's so that we get very high resolution. So, for example, I could call this one m equals 0, the central. This would be m equals 1. This is m equals 1. And I would get a diffraction of X-rays that looks like like a diffraction grating. And it's the same pattern that I get with a grating. And using those two hypotheses, he said, aha, this is what I should observe. Of course, n equals 2 here, and etc. Right? So that was the general idea, that we can actually do that. Now, in the actual experiment that was done, I'll try to, other side okay? Okay. I'm trying to think whether I can erase this, but yeah, let's go here. The actual experiment that was done was actually shown here on the slide. So I think I can actually point to this better. You also have a picture of it in the lower right side of the handout on the first page. And basically the idea was the following. Instead of allowing my X-rays to be transmitted through the bottom and penetrating up, and of course the X-rays get reabsorbed and they emit it in rays in different directions as they re-emit the excitation, the light from or the X-rays from the de-excitation of the atoms as they re-emit their wavelengths. Instead of doing that, where light is coming up from the bottom and transmits through, what he proposed was what we call a reflection experiment. The reflection experiment is that we will bring X-rays in from the side at a certain angle with respect to these crystals, and they will, in general, they will be emitted and re-emitted, or will re-emit into all directions as they scatter off of each one of these atoms. The point that he was emphasizing is that there are special or particular angles which, if you direct those the rays into the crystal lattice, that you don't just scatter randomly in the backward direction, but there will be certain angles of the X-rays which preferentially will emit an angle phi, which is identical to at the angle of reflection, which is identical to the angle of incidence. So the idea was that that for certain angles phi, there would be an enhanced reflection, or a maximum intensity of the reflected rays. But they only occur at special angles. There's only a few angles in which I get this selective interference or increase in reflective intensity. And the idea was similar to what we've been doing with path differences with double slit and multi-slit. And the idea was that if you look at rays that are reflecting off of the surface of the crystal, and if they are incident at some angle phi, and I look at those rays that are reflected at the same angle phi relative to the horizontal, that in certain conditions I will get a huge number of reflections at that angle. At that angle, the intensity of the reflection will be enormous. At any other angle, it will be 0, right? Or we will say close to 0. And the condition was that if these rays, which we now call X-rays, were acting like waves, which we are assuming that they do, it's just another electric field that's oscillating up and down, moving along the axis of its propagation, then there will also be rays that reflect off of the second layer of the atom at that same angle phi, and there will be a path difference between rays reflected off of the first layer and rays reflected off of the second layer. So if I want to know what is the difference in path for those two, then what I do is to look at the perpendicular dotted lines drawn off of the atom I'm pointing to, and look at the line segment from this point to the second layer of the atom, and from the second layer of the atom back to this point. And this distance is equal to d sine theta. It is equal to d sine theta. So the ray that reflects off of the second layer goes a distance d sine theta further than the ray reflecting here, plus another d sine theta on its return path. So the total path difference is going to be equal to 2d times sine theta. So if the difference is, so if the path difference, let's see if I can use another chalk. So the path difference is equal to 2d sine theta, then the phase difference is equal to 2 pi over lambda times 2d sine theta. I'm sorry, it's just sine phi. Let's use the same nomenclature as the angle in the slide up above, and I'll draw it this way. And when this phase difference is equal to m times, or I should say m times 2 pi, then I will get constructive interference. This will give me constructive interference, and I will therefore see a peak in the intensity of the reflected X-rays at that angle. So these will be particular angles. Because it depends on m, I'll put a phi sub m here, because it's now quantized by this condition right here, that the path difference has to be equal to some multiple of 2 pi. And so if I simplify this, I should get that 2d sine phi sub m is equal to m times lambda. Okay? Is equal to m times lambda. So whenever the path difference is a multiple, integer multiple of the wavelength at that angle, I will get a huge spike of intensity of the reflected light, or the reflected X-ray. Okay? At any other angle, I will not see any, there will not be any constructive interference. And so I might, in fact, just see kind of a uniform background or no intensity at all. But I can draw you a picture of it that actually might explain it a little bit. But while I'm doing that, or before I do that, I'll stop for questions. Does anyone have a question before I continue? So the basic idea now is that if the X-rays are coming down and they are reflecting off at some angle, that here is my X-ray source. By the way, if you've ever wondered about an X-ray source, you experience them every year when you go to the dental office and get your X-rays done for your dental work. We can talk about X-ray production hopefully in a future lecture. But for right now, what we have is an X-ray source that is generating, that comes in at some angle phi. And whenever we have a condition, so if I now swing my detector, or I might even use film, you can actually use photographic film, or I swing my detector, my X-ray detector, around from 0 to 90, then when I have the condition that 2d sine phi equals to a multiple of lambda, then I will see a huge spike in intensity. So this is intensity, and I'll call this angle theta, because I'm going from 0 to 90 degrees. And whenever, let's say, for example, let's do it this way, 2d sine phi is equal to 2 times lambda, then I will get an intensity maximum right here. And if I lower it down to, and I'll call this phi sub 2, and I'll make this phi sub 2, then I will get a maximum reflected intensity. X-ray intensity. Now, if I want to go to a smaller angle, for example, one where I'm coming in, say, for example, down here somewhere, and now I come in at another angle phi 1, there will be another angle phi 1 where I get 2d times sine of phi sub 1 is equal to 1 times lambda, and this will be the first intensity maximum. And in that case, I will get a reflected intensity maximum that occurs right here. So this will be for m equals 1. And this will be for m equals 2. So it was a confirmation that X-rays act exactly as waves, electromagnetic radiation, which is the same phenomena as a light wave. It's just that the wavelength is shorter. Right? So that was the first confirmation. The second thing it confirmed was that simple cubic lattices really did exist, and if I had an independent means of finding the spacing between the atoms, then I could actually confirm that these intensity maximums occur at these angles. Now, at the time that the measurements were actually being done, one thing that they could certainly confirm was that there were selective angles sine phi sub m, which was equal to m lambda divided by 2, and that those selective angles were in fact producing intensity maximum, I'm sorry, divided by 2d. That those angles were, this is a measured quantity. We start with small phi and work our way up from 0, so we can find where the first, second, and third maximum occur. But all we can really tell from this is the ratio of lambda over d. Okay? And it took further experiments to later find out how to measure lambda a different way, or how to measure the spacing a different way, and then we could confirm that in fact that the rule of this is called Bragg's law. So this quantity, or this equation right here, is what we call Bragg's law. But Bragg's law of X-ray reflection, right? X-ray or X-ray diffraction. Okay. There are only selective angles where this can occur. Is there a maximum angle? Can we calculate what is the maximum angle that one can actually observe an intensity maximum at? Well, we'll see that in the next slide. I'll try to work that one as we go on. Any questions on this so far? Bragg's law, X-ray. Now, the reason why we're doing this and spending time with this is that at a later time, the same experiment was done with electrons, with protons, and with neutrons, and the same relationship was found. Right? So what we're going to find out that when later in quantum theory, that when we deal with electrons, protons, or neutrons, that they also act like waves. They also have wave-like interference, wave-like interference, and of course diffraction. Now, and therefore, we can say that they also have a wavelength. They also have a wavelength. They also have a wavelength, because we will show that in chapters 40, 41 when we get there, that you can repeat this experiment with particles and show that they also act like waves. But we first have to show that waves act like waves, or what we think are X-rays, or waves, which in this case is X-rays, act like waves. And then we can say, oh, we've done this now with real waves. Let's see what happens when we do it with a beam of electrons or a beam of protons. And the idea is that we will find out that they also have, they actually give you these same diffraction peaks. But we need to know how to calculate the wavelength for the electrons, which was a different subject, which we'll get to later. But it's important because this is a foundation for understanding the quantum theory, and that's why we're going over it. Okay, so that's Bragg's law. So let's try to work a problem. So you can read this while I'm getting my papers together. I think I'll go ahead and erase this, because everybody got this down all right? We're good with this? You want that? Okay. Is everyone done with this over here? This side I can erase. Right? All right. So, so hopefully everybody gets the analogy here of crystals act like a diffraction grating, and X-rays act like waves. Okay, so let's read this problem here. Suppose we have, I need my pointer. So we have, suppose that X-rays with lambda equal to 0.1 nanometer are scattered from a sodium chloride crystal. A second order diffraction peak is observed at some angle, we'll call it 21 degrees. What is the spacing between atoms in this simple cubic crystal? Well, we know that we have a unique Bragg's law to use, so we'll just write down that 2 times d times sine phi is equal to, and let's see what I said was here, with a second order diffraction peak, so that means that m is equal to 2, so this becomes 2 lambda, this becomes phi sub m, so I basically solve this for d, and I get that d is equal to lambda, d is equal to lambda divided by sine phi sub 2. And by the way, m is equal to 2 in this equation, so I can put here, this is the second intensity maximum, and this becomes 0.1 nanometer divided by sine of 21 degrees, and this becomes 0.28 nanometers. So the spacing between the atoms in the sodium chloride crystal, which as we know is also called table salt, right? Salt is sodium chloride. The spacing between the atoms in this simple cubic lattice is 0.28 nanometers. Okay. Now the second question is, at what maximum angle will we observe a diffraction peak? So in other words, we start at phi equals 0. we change the angle of the beam until we get say, an intensity maximum on the other reflected side. Then we increase it again, we get another intensity maximum. We increase it again, and we get another one. How many times can we do this? Well, we've used this criteria before, but we know that in any given equation, that sine phi sub m must be less than or equal to 1. Right? The sine of any function, of any angle has to be less than or equal to 1. And because the fact that we know then that by this equation, this is lambda over d, then we know that sine theta m, this says that sine phi sub m equal to m lambda over d must be less than 1. I'll say less than 1 because if your X-ray source is exactly at 90 degrees, then your detector cannot also be at 90 degrees because they can't occupy the same point in space. So we'll use the inequality here. Let's see, right? So what is the maximum angle that one can observe a intensity maximum? And we just have to put some numbers in, right? So now we say, okay, lambda was 0.1 nanometers. So m times 0.1 nanometers divided by d, which is 0.28 nanometers, must be less than 1. So therefore, I will find out that m less than, is that right? Yes, the sine has to be less than 1, so m has to be make sure I did this right. Give me 1 second. M must be less than 3. Somebody want to try that on a calculator? Let's see. Yeah, because 0.3 is greater than 0.28. So m must be less than 3, which means that there are only two angles, phi 1 and phi sub 2. And at what maximum angle will diffraction occur? Well, we just calculated phi 2, right? Phi 2 was, we know that there was a phi 2 at 21 degrees. So can there be a phi sub 3? I don't think so, right? Because sine phi sub 3 would be equal to 3 lambda over d, which is greater than 1. Right? So there are only two maxima angles at which we can get an intensity maximum of the reflected X-rays occurring in these are phi 1 and phi 2. Let me make sure I did this right. I made a mistake. I said I didn't catch this because I was looking at my notes and I thought my notes were right, and I said my notes are wrong. I made a mistake. So let's go back. If I take this again, I really forgot to put this factor 2. So this becomes m lambda divided by 2. So now I have a factor 2 down here, which means that m must be less than 6. So the largest I can have is n equals 5. Everyone see that? I left out a factor 2. Okay. So I was wrong. You can have 5 angles of incidence with 5 maximum peaks of reflected intensity. Right? And everywhere else, at every other given angle, it will just be either 0 or a low background of X-rays. But you'll see this huge intensity spike at these selected angles for the reflected rays. And at any other angles, you will see nothing. Or some very small amount of background. Okay? Yes?
When you're calculating m, you want to round it up to the nearest integer? Or could we put a decimal answer? Because the decimal answer I got was 5.6.
Right, but m has to be an integer because this has to, in general, Bragg's law says that the 2D sine phi m has to be equal to m times lambda, and m has to be an integer. Otherwise, you will not have constructive interference, you know, between those two rays, the reflection, right? So you have to round down.
Okay.
Right?
So it would actually be n is less than 5?
No, this says that, well, let's see, you're right. So you calculate this to be 5.6, correct?
Yeah, 5.6.
Oh, I'm sorry. So you calculate m equal to 5.6, right?
Yeah.
But m has to be an integer. So what's the largest integer?
5.
That this, yeah, so the largest integer that I can get is, you're right. So let's say, maybe put this way, m is equal to 5.6, but m cannot be a decimal, it has to be an integer, therefore I have to have round down, and the largest, so I say m max, the maximum value of m is equal to 5. How's that? Okay. So if that's true, I can say what angle, at what maximum angle will I get a diffraction peak? Well, I'll get the maximum, the angle has to still satisfy the Bragg equation with m equals 5. So I have to have that sine phi sub 5 is equal to 5 lambda divided by 2d. And I know what lambda and d are, right? So this is, lambda is 0.1, d is 0.28. So I get that this number is 0.89, and so phi sub 5 is equal to 63.2 degrees. And there's my answer. So that's the largest angle at which I can point that X-ray at the crystal and get a maximum intensity of the reflected rays. Or get a peak of reflected intensity. Think about it. Okay. Hand or okay. Someone has to say yes for me to go on. Okay, good. All right, good question. Yeah. Is it clear?
Yeah.
Is it 80% clear, 50% clear?
Yeah, so we're just a quick question, we're gonna plug that M back into the sine theta equation.
Yeah, that's what I did here. So I said the maximum that m can be is 5, so I put right in here m equals 5.
Okay. Yeah.
And so that's the maximum angle that I can point the X-rays at the crystal and get a maximum reflected intensity of.
Okay.
Get a peak of intensity. It's like any other angles, you just kind of see nothing or just kind of like a smooth background, and then boom, you hit that one angle, and suddenly you look at the other reflected at that same angle in the reflection part, and that's where all the X-rays are going.
And then, so using that number, I can find out what other angles I have. So say I have an angle 2.
Well, m equals 2 was this one, and that gave us
21 degrees.
That was 21 degrees.
Okay.
That was given to us.
Yeah.
I think it's pretty clever. It was worth a Nobel Prize. It's one of the few things you can actually explain in a class in this short a time. But it was, yeah, one of the Nobel Prize experiments of the 20th century. And of course, today actually this technique was used to discover the molecular structure of DNA, which Watson and Crick got the Nobel Prize for in 1950 something. They did their experimental work in 53, and they were able In this case, what we've done is taken a simple cubic lattice where we assume that all of the atoms are equally spaced, right, on a cubic lattice. You can use this when they're not uniformly spaced, and if you take X-ray reflections from enough different angles, you can reconstruct the atomic spacing of very complicated molecules. And this is what Watson and Crick did to discover the double helix. They used X-ray diffraction experiments off of DNA molecules to find out what the helical structure of it was. Obviously, it's much more complicated than this, but this is just like the background. All right? Okay, so you've got a couple questions on this in your homework for Friday. I think I'll move on because I want to get to the last subject matter of the chapter that we are going to cover, and I will try to come back to this. And that is what we call the limits of spatial resolution in optical devices. So let me do a little bit of erasing here, and this. Yep. I'll try to do it this way so that if there's still parts that have not been copied yet, you still have a little time to put those into your Okay, so the final subject of this chapter that we're going to cover is spatial resolution. And for that, we will look at your second handout, which starts with the page, not with the eyeball, but with the page that says diffraction through a hole with parallel light. So this is the way we'll start approaching this and try to make this as clear as possible. So there is a limit of resolution that one can achieve with optical devices. For example, the lens of your eye has a certain limit of optical resolution. The lens of a camera, the lens of a microscope, the lens of a telescope. And basically what we mean by resolution is what is the smallest distance between 2 points of objects which are still resolvable by the eye or the instrument. Right? So in other words, we know from experience that if we took 2 specks of dust that were individually, visible, but yet small enough to fit on the top of our thumbnail, we can visually see that. But if we brought another one that we can also see and bring them close enough together, at some point we cannot see that there are 2 that will appear as 1. The same thing's true if you have 2 stars in the sky that are extremely close together. Then there is a limit of optical resolution which says if these stars are closer together than a certain distance or angle x, they no longer appear as 2 objects, they appear as 1. And that is because each one of those is going to get blurred out by the optics. So there's what we call the blurring effect, right? And the blurring effect is what keeps one from bringing 2 objects of very small visible size infinitesimally close together and still being able to resolve them. Right? In other words, each object gets blurred, and what we actually see with our eye is 2 blurred objects that each have some blurriness that then merge into one blob, one blur, right? So that's the idea of what we're discussing here is when we talk about resolution is how close can we bring 2 objects together and still resolve them as 2 objects before they start appearing as 1. Okay? So we'll give a couple examples of this. Let me turn the lights down a little bit so we can see see the slides, I'll go back and forth on this. This is the definition of the resolution. And this blurriness that we get from objects going through lenses can be due to several different things or phenomena. One of them is what we will call the diffraction limit. But the other one is, others that are related to resolution, is how many pixels do you have in your camera? Okay? You know that if you buy a 10 megahertz, what are they making now? They make 10 3 megabyte pixels, 7? How high can you buy it? What?
Smaller and smaller.
Yeah, but I mean, there's like a limit to what is commercially available. Something like that. So it's typically at the order of X megapixels, right? So any picture that you take can be broken up into tiny little pixels, and that pixel is the limit of your resolution of your camera. Right? You cannot observe any two objects that are small enough to fall within the same pixel will appear as one object. So that's one example of resolution. How many pixels do you have on your detector? The other example is that lenses have what's called aberrations. In other words, in elementary optics, you learn that if I have a point object, I'm trying to do it with my hands or on the board. If I have a lens and I have a point object here, it will get focused onto a point object on the other side. And that's called point-to-point focusing. Now, in actual fact, the lens creates, and you're looking at rays that go through every part of the lens, and they converge to a point over here. Right? But lenses are not perfect. And so what happens is they don't all perfectly converge to a point. They converge to a circle, a blur. So a point object can only get focused to a blurred object. The blur could be very small. It could be imperceptible to you, but there are distortions due to the lens, the optics of the lens that limit how precise you can image one point here onto another point without letting it get blurred, right? Or how large will the blur be as a result. The third one that we're going to talk about is the limits of resolution, or the blurriness caused by the imaging of an object due to a lens or to an optical device. So we know from single slit diffraction experiments that the intensity as a function of angle has a minimum at plus lambda over d and minus lambda over d. And then these intensity maxima die out as you go further away. This is what we call the diffraction from a single slit. Now, if we replace the single slit with a hole, a circular hole of diameter d, then it turns out that these minima occur at a slightly larger angle, which is 1.22 times lambda over d. We're not going to go into the derivation of all that, but the idea basically is that you still get diffraction occurring from a hole in a opaque structure where only light can go through the hole. Right? There's still diffraction, and it looks very much like single slit, except you get annular rings. You get circular rings. These become rings of maxima instead of lines on the distant screen. Right? So diffraction phenomena occurs with circular apertures as well as for rectangular apertures. Right? And this is the phenomena that we have. Now, let's see if the next slide actually says anything about that. Now, okay. The Raleigh condition, or I'll tell you what, there you go. Let's go to the handout. Let me turn the lights back on a second, and let's look at the handout for just a second. On the left side of the page, the upper right, you see the diffraction pattern for a single slit experiment, right? And there's the central maxima, and then there are the m equals 1, m equals 2 fringes on the side. Right? Now, what we are going to state without proof here is that if in that hole, which is the hole where the light goes through, I put a lens in there. Okay, everyone see that? I put a lens here on the figure on the right side. There's a lens there. Now what I'm going to do is I'm going to image a point of light, or a point source, I should say, onto a distant screen by focusing the light through the lens. And if I use geometrical optics, I can locate where that point of those rays are going to converge. And that convergent point will be the image of the object. In a perfect world, that point object, through reflected rays going through the lens, gets refocused to a point, and so the object point goes through the lens and produces an image point. Okay? In a perfect world, it's a point-to-point focus. But we just said that there are several reasons why the point object here cannot be focused to a point. It's going to be focused to a blur. The blur may be very small. You may not notice the blur, but there is a blur. In other words, there are limits of resolution because the light does not all get perfectly focused from one point to the next. Okay? Also, we talked about pixels, right? Let's suppose your pixel size is 0.5 millimeter by 0.5 millimeter, and your light occurs, you detect the light, you have a pixel detector, and in your pixel detector, you detect the point here. But your detector doesn't know where in that square that light arrived. So it says, oh, I'm going to put it right there. That's the best approximation based on what I know. There was a signal on this pixel, but I don't know where I'm going to put it in the center. Right? This is going to give you a blurring effect. Okay? And your eyes work the same way. Your eye is a pixel detector. It has finite resolution. There's a finite number of these pixels. And if this rod lights up from here, it's going to look the same as if it lights up on the other side of that pixel in your eye. Okay, so that's a form of blur. But the form of blurring that we're talking about here is the blurring due to the diffraction of light going through the hole where the lens is located. And basically what this is saying, and we're stating this without proof, that the blur of an object going through a lens of diameter d will have an angular blur with an angular uncertainty, or width, so if I look at the image of this object right here, so I'll put a point of light right here above the axis, and it's going to get imaged to a point below the axis this way, then this is not going to get imaged as a true point, but it's going to have a blur. Right? And there's going to be a certain width to this blur, which is called delta theta. I call it delta theta 0 or theta min, which is the smallest width at which this light can get focused. This is a diffraction maxima, so this is a resolution or width due to, or I'll say width, due to diffraction. And the diffraction width or blur, the diffraction width or blur is equal to the width of the central maxima of a diffraction of light through a hole of diameter d. So if the lens aperture, or the aperture which I'm making a focus, has a diameter d for this lens, for this light to go through, then this angular blur will be equal to 1.22 times lambda over d. And this tells me, excuse me, this tells me what the minimum angular width of the blur is coming off into the image. The image has lost its point nature. It's no longer, this is the object, and this is the image. The image is not the point. The image is this intensity profile. It's been blurred out. And the amount by which it's been blurred out is 1.22 times lambda over d. That's the angular width of the blur. Okay? Now, what happens if I have two objects and I have another object right below here, what did I say here, and it's going to get imaged right here, and it also gets blurred out. Then I'm going to have some, we'll call this spacing distance S, which is resolved into these two peaks, which are separated by some other distance, which we won't talk about right now. But the point is that I can see that they will separate into two objects. Now, in the limit as S goes to 0, right, then these two peaks come together, and the two objects blur, two objects are imaged into one blur, not two. Right? Everyone see that? If these intensities come back to these two peaks, if these two get smaller and closer to the central axis, these two get closer to the central axis. So these individual peaks are going to be like this, and another one that looks like this. And when I add them together, I get this. They no longer are two, they are one. Kind of like the marriage vow. Okay, you get the idea here? These things are actually get melded together because you're adding two Gaussian peaks, and you add them, they get close together, they're going to look like one Gaussian peak. So what's the minimum separation that one needs in order to resolve two individual peaks? The minimum separation we need in angle, and here we're talking about this angle, delta theta 0, is going to be given by 1.22 times lambda over d. So this is the limit of resolution that can be obtained from due to diffraction. Okay, so what is the minimum separation at which I can observe these two objects as two independent objects? Well, if this is the minimum angle, if the minimum angle that they can be separated by is 1.2 times lambda over d, then that means that when this angle theta, we'll call this theta, right? When theta is less than theta min equal to 1.22 times lambda over d, then the objects are unresolved, right? I can't tell the difference. The objects are unresolved. Okay, what is that limit? Okay, what is that? Well, how do I calculate S then? If this is the minimum angle, what is the S minimum? What's the minimum S min is the minimum separation to resolve two objects, right? That's basically it. This is object 1, and this is object 1, and this is object 2. Right? Well, the minimum separation is going to be S min is equal to the distance L of the object to the lens, so let's call this distance L, is going to be equal to L times tangent theta, times tangent theta min. Right? By the way, strictly speaking, this actually has to have a sine theta in here, but in fact, in all of these cases, in all of these cases, we'll be dealing with extremely small angles. So we're just going to say this is equal to L times theta min. And that's the minimum separation that one can have. Okay? So the minimum separation for any optical device for limits due to diffraction alone is given by this equation. Right? That's the best you can ever do. And the only way you can do better is to make the aperture bigger. That's the only way you can make the resolution better. Right? And it turns out, like for example, some telescopes in the sky, the apertures are over 2 meters across. We have lenses that are over 2 meters in size. So we'll do an example of one of those, if I can find it here. Supposing that you had the Hubble telescope in space. That one happens to have a lens diameter of 2.4 meters. That's a lens that's longer than the stretch than the length of my body. Suppose that Hubble Space Telescope was turned its telescope around. The telescope was turned to point towards the Earth, and it's flying at an altitude of 600 kilometers above the Earth. Right? What would be the minimum separation that two objects could be just barely resolved by this telescope? So here you see the blurring effect, right? Object 1, object 2, they form an image, they each get blurred. This separation has to be at least bigger than or equal to some angle theta min. Theta min is 1.22 times lambda over d. So what is the minimum separation that the telescope could barely resolve these two objects on the Earth? Okay, so we'll do an example of that, and it turns out to be a pretty simple one. Is equal to L. So L now is the distance from, this is the Hubble telescope. This is the Hubble lens. And it's sitting at a distance L of 600 kilometers above the Earth. So the minimum separation that it can resolve, this would be L times theta min, is equal to 6 times 10 to the 5th meters, so this is 600 kilometers, right? Times 2.8 times 10 to the minus 7, and that would be in radians, so this number is 0.17 meters, which is equal to 7 inches. 7 inches. From the distance of 600 kilometers, roughly 400 miles above the Earth, the telescope can resolve two objects that are only 7 inches apart, from hundreds of miles away. This is extremely good resolution. Right? Now it turns out that this is also the resolution for spy telescopes. Everyone seen those images of, when we want to know Saddam Hussein or some foreign government, are they moving tanks around? Are they can we see objects getting moved on the ground? And what if their car is only their object that's 7 inches, but let's suppose it's a tank that's 3 meters big, 3 meters long, wide, whatever. Can it see it from a distance of 400 miles above the Earth? Yes, because it has a resolution of 7 inches. Now, if those two tanks were closer together than 7 inches, then they would look like one large wide tank. So in other words, the spacing between the objects has to be this much. But that's still pretty good. And in fact, if you ever seen pictures of spy telescopes, and there have actually been some movies with them, these lenses are huge. They're like this. They're meters across, because you need that resolution to be able to see something on the ground. Right? So lens diameter is extremely, extremely important for that. And of course, the only way you get better resolution is to make it bigger diameter. So, any questions on that? Any questions? Yes.
Where does the number 1.22 come from in that equation?
There's a derivation, but the book it makes a plausibility argument. I mean, it comes from actually doing an integral of all the wavelets from every point on the lens. So basically, you remember Huygens principle says that light is, there's wavelets that are being generated, that are wavelets that are being generated from every point. Remember how we divided the slit into subslits, right? Well, I can divide the circle into subcircles. And I can consider light emanating from every point on that circle. And then I have to add them all up. And that's a humongous integral that we don't want to see. Right? Especially since the answer is so close to the single slit experiment anyway. Right. Good enough? Is that fine? Okay. Okay, one more example. We've got time for eye resolution. And so this one is kind of interesting. I think it might be on the back side of your, let's look on the back side of your handout here. So on page 2 of the optical resolution sheet, what you see here is, let's suppose that you want to find out what is the minimum distance between two objects that your eye can resolve. Now your picture is shown right here, so I don't need to probably redo it that much, but I'll try to do as much as I can anyway. So here's my eye, and here's my two objects. And here's the image, which makes a blur. And then this image, or this object, makes an image that's a blur over on this side. And I want to know what is the minimum separation between these two specks of dust that S-min, in which they are resolvable. And the basic idea for doing this is that I need to know what is the minimum angular separation between these two peaks to be able to resolve them into two different objects. So we use the same equation, only now the distance L is going to be the distance from my lens to the eye. So L is the distance from the object to my lens. And the formula that I want to use is the same as before, is that S min is equal to L times theta min. Right? And now all I need to do is calculate both of these. Right? Well, L, what is L? L is called the near point of your vision. The near point is how close can you bring your finger to your eyes and still keep it in focus? Right? It's not here. And for most people, that near point is about 20 or 25 centimeters. Okay? So the closest that you can actually bring your finger and keep it in focus is about 25 centimeters. Now, so we've got a number here for L, 25. What is theta min? Well, it's 1.22 times lambda over d. Lambda for the mid-frequency or wavelength of light is 550 nanometers. And d is going to be the diameter of the iris, of the opening. So this will be your iris. Okay? And your iris opening is going to be, well, it can be anywhere from 1 to 8 millimeters. Okay? depending on light intensity. Right? Let's take 1 millimeter and calculate what we get. If we put 1 millimeter in here, and I have a value now for theta min, I get that the minimum separation that your eye can resolve with 20/20 vision is about 0.165 millimeters. Okay? It's about 1/10 of a millimeter. And if you've ever held a ruler out and looked on the millimeter scale, and I asked you how close together could those lines be on the ruler and you'll still resolve them, you probably can't go much smaller than 1/5 of a millimeter before they gets blurry. Right? 1/10 of a millimeter is the best. So this actually gives you a pretty good description of how well, what is the resolution of your eye. And it only depends on the diameter of the iris. Okay? Now, it's quite a bit better if you go to 8 millimeters, but then of course you have to be in a very darker room, otherwise your eye would be dilated and it would be harmful. Okay, so this gives you another way of calculating resolution. Okay, you've got homework problems. I think you've got enough to really get through it. We'll try to cover a few more odds and ends, but we're going to start relativity on Thursday.